Okay, so good afternoon. We just crossed 12 afternoon. So I'll be talking to you on this LCO robotic telescopes. Basically, the idea is to what's it? Can you hear? Hello, clear, right? Yeah. So basically, the idea is data is available everywhere, and you have seen that you can get archival data from Gaia site and HST and so on. And here's one more possibility, one more option for all of us to actually take your own observations and get your own data, right? So LCO. So what is LCO? LCNO stand for this last Cumbres Observatory. So there are 25 telescopes at 7 sites around the world, and they work together as a single instrument, right? And you can get registered on the site and get observations. If you belong to an organization, if you have an NGO of yours or a group which is registered, then you get more time and more flexibility to do it because, yeah, but individuals can also get data from the, yeah. So, and yeah, so from, and the archives are available from where you can download data, and we'll have a look uh, what kind of data we get and what all can be done. So those spots, dots which you see on the map, uh, these are the places. There's one in Australia and China and Africa and Chile and so on. We'll see that map bigger. So this is LCO is a network of astronomical observatories run by a non-profit private operating foundation directed by Wayne Rosing, and it was started in September 2005. And the number of telescopes have been growing ever since. Its office is in California, and the telescopes are located both in the northern and the southern hemisphere and across time zones. So that makes it very convenient for us to observe, to track a certain event, to find, there are some transients and suddenly you get to know that you can observe it only from the southern hemisphere. So there are many telescopes in the southern and then time zones, since they are across the longitudes as well as latitudes, it makes it good to keep tracking an event and so on. Okay, so a variety of things can be done. So there are these 7 sites uh, in Chile, South Africa, Australia, Texas, Hawaii, Canary Islands, and so on. Okay, so these are the details, and you just search for LCO astronomy, and you will find more details on it. So, what are these robotic telescopes? So, a robotic telescope is a telescope which can make observations without any hands-on human control. So it runs in 2 modes. One is uh, a scheduler, a manned scheduler provides an observing plan for observers, human astronomers, to start the each night. And then it goes into the robotic mode and it carries out automatically. So you set your target, you set your dates. You can say if you are looking at a certain object from a certain day to another, you set your parameters, what kind of exposures require, and it does it. So depending on where it's available, it finds it and gets the data and puts up on your in your bin, and you can download it. And after a while, it becomes open for others to use. So as individuals, probably you will have, if you register, you may have problem scheduling it, but we as this organization, we run a Srishti Astronomy. So we are part of this LCO group, and we can get data for you. If there's something interesting, there's a comet which appears, or a gamma ray burst or something, and you can contact Priya ma'am, preferably her or me. Um, so we can do it for you. Yeah. So the purpose, why is this unique? The purpose is to build transient astronomical events whose duration can range from seconds to several years. And like we have discussed, it's a global distribution of telescopes across longitudes and latitudes. And there's dynamic observation scheduling. So scientists can make requests for observations at any time, and the scheduler updates the entire network plan about every 5 minutes. The scheduler keeps checking what requests have come, and it catches the object if it's available on any of these sites. Um, so uniform, and then one good thing is the instruments across these telescopes are essentially uniform. So and and the data is also, there's rapid delivery of data which comes within minutes. So you can see these 7 places clearly now. Australia, in this is Canary Islands, Africa, South Africa, and so on. Okay, so these 7. So as the sun rises somewhere, it sets somewhere else, and depending on what object you are, you can keep observing it. Okay. So LCO has the details of this can be found on the net as well. But basically, it has purchased 2 twin Fox telescopes in 2005, and one is in Hawaii, and the other one is in Australia, and that has spectral camera. It has low resolution spectrograph and this Muscat camera. Okay, so you can see the animation of how the dome opens up and it's taking observations. Okay, so there are 13 1-meter class telescopes. Yeah, those were 2-meter ones. And there are 13 1-meter telescopes. And some more, they keep getting added on time to time. All of those 1-meter telescopes, except one, have this Sinistro imaging camera. And 4 of the 1-meter sites, which are listed here in McDonald's Observatory, Wise Observatory, CTIO, and so on, also have high resolution NRSC spectrographs. Okay, so the instruments which are there with this 1-meter telescopes are listed here. SBIG red camera, Sinistro camera, focal length and details, 4K by 4K, FOV of 26 arc minutes with 18 filters and so on and so forth. These are all listed. These are the instruments which are available there. And there are 10 0.4 class telescopes, 0.4 meter class telescopes, and which are deployed in various observatories across. So a typical, and these 40 centimeters or 0.4 meter telescopes have these instruments on that. SBIG silver camera, 2K by 3K with FOV of 20-30 arc minutes with 12 filters, and LIHSF fast camera for auto guiding, fast photometry, and lucky imaging and FOV of about 10 arc minutes, square minutes. Okay, with 5 filters in it. Okay, so this is a site, typical site looks like that. You have these are three 1 meter telescopes which you see there. I think this is run out of power. Okay, so yeah, so you can see that these three are 1 meter telescopes, and then you have six of 0.4 meter telescopes here, and you have a storage. The data goes into that and then gets distributed. Okay, so all these function robotically. Only scheduling is done. Yeah, we put in our requests, and they handle a little bit of manual intervention goes there, and then once they are scheduled at the correct time and correct, you get observations in whatever filters and so on you require. So there are other Noir Labs and SOAR, Gemini. They are all working together. They are planning to build a consortium where these small telescopes scattered all around and larger facilities can be integrated, and phenomena, events which are happening can be followed up, either found, detected from these, and it informs the larger telescopes to see these targets of opportunity or targets of interest, right? For example, you are doing a search of exoplanets. Yeah, many have done projects with exoplanets. You look at these transiting ones and so on, and if they are interesting objects, then you can these smaller ones, since they are scattered all around, and you can use them all the time. Once you find things of interest, then the bigger facilities can be put into action to observe that in more detail and so on. Okay, because the big telescopes, the observation time is very expensive. It only goes for proposals which are very, very important. Okay, so this LCO Mars it makes alerts really simple. Yeah, if there's an supernova comes up and one of the telescopes catches it, you make an alert of that. Then you have that AEON, which is Astronomical Event Observatory Network, and this Storm Toolkit. Okay, so they all function together. And so this Las Cumbres Observatory Global Telescope Network, LCOGT, is a collection of all these telescopes which are yeah, and it's a very important education, and they're providing a very large education content and so on. Okay, so coming to the data which you get, it goes through a Banzai pipeline. So when we go to the site and have a look, you will see that you can either find raw images or you can find processed ones. Yeah, it goes through a pipeline which is called the Banzai pipeline, and yeah. So basically, what is photometry? Photo from the Greek word light, and metry is measurement. So it's a technique which is used in astronomy that is concerned with measuring of flux or intensity coming from these celestial objects. And then you measure the light using photometers or CCDs or so on. And then you have to calibrate. If you know certain standard stars, then you know what their magnitude or the luminosity is. On the basis of that, you can calibrate the other ones. Okay. So what we observe from a certain particular site or place on Earth is called apparent magnitude. And many of you probably are familiar with what is apparent and absolute magnitude. Apparent is what appears to you, and absolute is what it actually is. So people have decided that to place all objects at 10 parsecs away from you. 1 parsec is 3.26 light years. And the luminosity which you would observe if it's kept at 10 parsec will be the absolute luminosity. The luminosity of a star, it depends on the radius of the object. It goes by that formula, R square, and uh, temperature. The hotter bodies are brighter, they are more luminous. So it's 10 t to the power of 4. And uh, so having the same temperature, if the radii are different, smaller ones will obviously be less luminous, while the larger ones will be larger. Okay. So one thing is the actual luminosity which is coming out of a star, which depends on its temperature and size. But the other thing is the distance from us. Yeah, if it's closer to us, it will look brighter, and if it's further off, it's cooler. Other than that, you also have to incorporate corrections due to interstellar absorption and make other corrections. Okay. So to get the actual, right? So there was a time when people thought that all stars are equally bright, the time of Herschel and so on. And they made mistakes about the size of our galaxy and shape of the galaxy and so on, because they assumed all stars are equally bright and there is nothing between us and the stars. So if something looked fainter, they thought they were far, while something looked bright, they attributed to keeping it closer. And they had made some maps of what galaxies look like, and they were uh, absolutely wrong from what we understand them today in terms of size. They were seeing probably, 1/100th of the galaxy and thought, yeah. So so what we realize today is stars intrinsically can be hotter or cooler. The temperatures of the photosphere can range from 3,000 to 40,000. And then sometimes a star which probably looks, the color actually indicates the temperature. So hot stars look whitish blue, while the cooler ones, relatively cooler ones, they look redder. But you can have interstellar absorption, which can make a very bright white star into to look red because of the scattering and absorption which the light would suffer if it goes to the medium. So all those have to be corrected to find out the brightness. And as you know, there is something called the magnitude of a star, which essentially means the brightness or luminosity. And since 2nd century BC, Hipparchus, he placed stars into these 6 winds, 1, 2 to 6, and the 6th one was the faintest one. One being the bigger number indicates fainter, and a smaller number indicates it's brighter, right? So it's slightly deceptive initially. So something which is minus 24 is extremely bright, while plus 28 is very faint. Okay. So one is your apparent magnitude, what we see, like sun is minus 26, approximately minus 26, full moon is minus 13, and so on. And this also gives us some kind of a scale of what you can see with what kind of a telescope. So up to 20th magnitude, one should be able to see with a 1 meter class telescope, roughly. It also depends on the pollution and the seeing conditions and other things, but roughly, and Hubble Space Telescope, they claim can see up to minus to plus 28, extremely faint. And the human eye's limit is 7th magnitude. Yes, 6th, and beyond that, we can't see. Okay. So this is what we have spoken about, and many of you are familiar with this distance modulus. Small m is apparent, capital M is absolute magnitude. So m minus m is minus 5 plus 5 log d to the base 10. And essentially this comes from the fact that between first magnitude and second magnitude star, the star is not half luminosity of the first one, but it goes by a log scale, right? So 2.5 difference between. So a 5 magnitude differences of star is 100 times brighter. Okay. So that's some simple. Okay. So in basic photometry, you are interested in looking at this image centering, estimating the background or the sky level, and calculating the flux which contains from the object of interest. So for example, you have this aperture photometry where you have the object, which is the inner circle. Then you have the inner sky and the outer sky. So there are various techniques by which you can do this aperture photometry. And this can be done through IRAF and so on, or it can be done through Python. Okay. So we may not have time to do photometry, aperture photometry on through Python, but if some of you are interested, over Zoom sessions or so, we can learn that. Some basic things which we are showing you, and we are showing you how to get resources from net. Either you can download these Jupyter notebooks which do photometry, and then just modify it for your objects, your requirements, and so on. Okay, so for example, you have a certain image. Yes, it was produced by this Stubbs as a part of High Z supernova team using, yeah. Outer sky. Yeah, so you draw annular regions and preferably of similar area, and you pick up the amount of flux which is coming out from that, right? So to define the extent of the object. So see, when you are taking an image of an object, you get light from the object and as well from the background. Whole thing is actually when you are processing by itself, is gonna take dark frames. Cameras where even if you don't expose it to light, it can give a signature on your on CCD. Okay, so you keep the shutters closed and you take dark frames. Typically, uh, on a CP, though the pixels are made very carefully, but the response of each one can be different. Right. So for that, the same intensity of light falling on a certain pixel and some other may vary. So usually what you do is you take flash. So in a observatory, you have either a screen which is uniformly lit, and you take multiple exposures to the same exposure time which you want to take, and you take images of a plain screen. And you construct a median or an average frame out of it. So that will tell you what kind of a response you are getting. So you divide your action by this field, and then you have to even subtract the sky. Then you take images of regions of the sky and see what is the sky brightness, and you do that. Okay. So essentially, to get what the brightness of this object is, you are getting light from the source and you are getting light from outside too. Try to understand how the brightness of the is. So here we have seen there are two regions where we are taking light, and you subtract those to get the actual one magnitude of the object. Okay. So there is a way. So your CCD by which you have these apertures in different regions. Okay. So here's these were two images from epoch 2 and 3 weeks later. And when you subtract those two, you see that all the stars and everything have disappeared, but only that this object has remained, which has changed its size. Right? You have taken two frames at two different times, and when you subtract one from the other, these objects have totally vanished here. But what has survived is the supernova era, and uh, that's something, right? And then the CCDs which we have are essentially black and white. It just keeps a collection of photons, counts how many photons are falling on a certain pixel and not. And by changing different filters, you get different amount of light which comes to you. So by taking it in blue and V and R, yeah, UBVRI is the Johnson-Bessel UBVRI filter scheme. And if you have at least two observations from two filters, you can find out the temperature of the star by seeing the difference between the peaks, right? So in each filter, it peaks at a certain wavelength at a certain temperature, right? So like, for example, red is more responsive around 600 nanometers, right? So very often it's important to take observations in different wavebands. So like we said, this LOC's Las Cumbres Observatory data goes through a Banzai pipeline, which stands for beautiful algorithms to normalize zillions of astronomical images, right? So Banzai is also a Japanese battle cry, a form of greeting used to Japanese emperor and so on. But yeah, so many of the time acronyms are given uh, uh, to places, objects, phenomena, which, right? For example, Python. Python name was given to that programming language because the maker of Python liked a series called Monty Python. It's nothing to do with the snake Python, but there's a comic series called Monty Python, and the person who made it was a big fan of Monty Python, so he named this Python, right? Like Aries. Conda becomes anaconda. Python, yeah. So from Python you have condas and larger distribution anaconda. Yes. Hmm? Yeah. The DS9 is a tool which is often used for images, to visualize images. And that's from the Deep Space Nine. Yeah. Monte Carlo, yes. Monte Carlo, yeah. So here you have this Banzai, beautiful algorithm to normalize zillions of. Okay, so we'll rush through. I have some 10 more minutes. Yeah. I have more than 10 minutes, but yeah, but I thought you will cut it short. Okay. So, yeah, I can go. So you have all these telescopes, 2 meter, 1 meter, and 0.4 meter telescopes, and it goes through this pipeline, and finally the data is available here. So with the images and the header information and all, you make these fits queued images, which go to the LCOGT headquarters, and from there it goes through this fits exchanger, and the raw data flows into the Banzai pipeline, and the processed data comes out, and then through this ingester it comes to the the archive books, okay, from where you can access it. So what does this Banzai pipeline do? During this processing, the following calibrations are performed: bad pixel masking, bias subtraction, dark frame subtraction, flat field correction, then source extraction from a frame. There are certain techniques of finding what kind of sources they are. You can have a cosmic ray which goes and hits there, or it can be an extended object, which is a galaxy, or a star, which is a point source. So there are various different methods, there are different programs which can find, extract sources. So from a frame, it picks up objects and classifies them looking at the point spread function of the light distribution at each point, and classifies them as galaxies or stars or different things. Okay, so it goes through this SEP. Yeah, so in Banzai it uses this SEP, which is source extraction and photometry, and yeah, so Python and C libraries are using to build this, and then it goes through this astrometric calibrations using this astrometry.net. So astrometry is, positioning basically of stars. Okay, so it gives a stamp to each frame, each object, and so you get to know what are the, from the pixel values XY of the image, you can find out what are the RA and deck of that, right ascension, declination, and the actual coordinates, right? Because frame coordinates are not very important for astronomers. Rather than, we would like to know what are the sky coordinates. So we have seen how to, right, get the sky coordinates from these. And then this Banzai pipeline finally, it is distributed in as a file which is uh, a fixed file, and very often you will see that they are zipped files. Yeah, so it has some name .fits .gz or some, we'll just have a look. FZ, huh? FZ, yeah. It has some, you will see that OGG0M406 KB12, this is dash E00 or E91. E00s are the raw ones, we'll have a look. .fits.fz. Okay, so they are distributed in this format. And then if you read those files, it has 4 extensions. We have the science data, SCI, BMP as the bad pixel mask. Like we said, on a CC, you may have pixels which are not responsive or spoiled or so on. There may be whole columns which are totally. So it gives you this bad pixel mask. Then it gives you the ERR. So Psi, BMP, ERR, and CAT. These are the 4 things which you will find. The array of cumulative pixel uncertainties, the errors which are there. And CAT, it gives you it creates a catalog which it gets from this SEP. And it shows you, catalog is a table where it gives you what are the objects which are there and how are they classified. Okay, on what XY coordinate and which region, what kind of an object is sitting there. So you have the catalog, the error, the bad pixel mask, and the science image. So the catalog lists the pixel positions XY, semi-major and semi-minor axis, position angle, and fluxes, errors of each source, right? So it's kind of a table, and you get the whole catalog of that. Okay, so here's an image of example of a reduced frame from Manzai. The left one shows some examples of raw frames, and the right panel shows the stacked processed image, right? In different filters to get these colors, which are basically artificial colors, but they are constructed with a certain sense uh, of attributing, which should kind of uh, should indicate to us what are the temperatures there. That's how these colors are given. And this is the see, look at the image which you have here, and finally what you have here. Yeah. So it after it goes by flat fielding and dark subtraction and size subtraction and so on, you finally get a good image. And there are many. Yeah, one good thing with a CCD is the response is very linear. So sometimes, um, uh, if you are taking, say, this image, there are certain objects which are very bright and certain which are very faint. So if your exposure time is less, it could only record the bright ones, while the faint ones would be gone. And if you give, say, a 40 minutes exposure, then the bright ones will saturate the whole, that the amount of photons it collects will go beyond the capacity of that pixel, and the thing will start overflowing, right? So since CCD response is absolutely linear, instead of taking 150-minute exposure, you can take 10 5 minutes exposures and stack them up, add them up. And when you add them, it works as though you have taken 150-minute exposure without overfilling any of these pixels, right? So, yeah, so this is the site from where you can get uh, the data of data archives of LCO, and and we'll go there in a minute. But in a very fast way, I'll go through science which can be done with LCO. A graduate student assisted in discovering a gas bubble orbiting a black hole, Sagittarius A, right? And this was done using LCO. Time domain astronomy, uh, these kilona, kilonovas was discovered by first using the LCO. Yeah. So initially, the Fermi satellite detected a region which is pretty. You see the just yeah, the Fermi satellite dictated gamma ray bursts coming from this area of sky, this outer red region. Then the LIGO and the Virgo detectors, using the triangulation method, they found that it is somewhere here in this area. And the LCO, it finds this kilonova, which is sitting right here. So right, exact position. And it could be done because there are so many telescopes and you are observing it at different times. And these kilonovas are basically transient astronomical events which come in two binary, very compact binaries, stars collide, or right, or a neutron star and a black hole when they merge. So these are bursts which last for a short while and then they die down. So this was again discovered using, exact location. This was discovered by the Fermi satellite, but once it was found that it's somewhere there, LIGO pinpointed a closer region, and then these LCOs were used to exactly find the location, right? So it can, with these 2-meter class telescopes, you can do really good work. August 2017, alert of a neutron star merger was given by LIGO gravitational waves. Yeah, but it's the same one. And yeah, these are the details of how they found that object. You see that 2017, 18th of August 2017 at 12 o'clock 15 minutes in the night they were found it. Okay. And uh, LCO can be used to detect and study exoplanets using these three methods: microlensing, transiting, and radio velocity. And LCO instruments vital to discovery of two super Earths. Yeah, these were used. And in July 2021, you had one such, and okay. And then the follow-up things were done by James Webb Telescope and so on, right? So this is an extremely powerful tool and good ones, and many a times students and people can uh, uh, play a very vital role in discovering very important events. Okay, so uh, you have citizen science projects to observe transiting exoplanets, planets outside a solar system with these small telescopes. Uh, Transit observations of exoplanets is important as using that you can directly measure the planet's radii and its composition. Exoplanet watch will help increase the efficiency of exoplanets studies by large telescopes and to characterize the atmospheres of these planets and various other things. Okay. So then another interesting was LCO telescopes captured the DART asteroid impact. NASA DART, you must have heard of this DART mission. The spacecraft which impacted an asteroid, Dimorphos. So there are many menacing asteroids which can come and fall on Earth. And there is a constant vigil which is trying to monitor them and look at them. And one of the issues is that if one major object is coming our way and we know it's going to come, what do we do with it? So people feel, some say that you should blow it up before it enters. Yeah. But you have to blow it up at a distance, and actually even if you blow it up, it will continue to come in the same trajectory and those objects will come and fall on us, right? Or give it a small nudge to it at a proper place, proper time, give it a thrust so that its orbital elements change and it gets diverted and so on. So but there is a threat. It has happened in the past, it keeps happening. So so this was one of the missions to see how hard an asteroid is, whether we can actually land and impact it and blow it up. And on September 26th, at 4:41, uh, when was this? This was in which year? That mission, that. And it went and impacted it. And as it, uh, that cloud of, as it impacted the object, the dust cloud which came up was observed by an LCO at South Africa. Okay. Okay, so with this probably I'll go to the site. Yeah, this is just to show that there are various global partners, global sky partners, and Srishti Astronomy is also a part of it. And basically, we want to use this platform and observations of LCO for educational purposes. Students can get a hand of actual data, learn processing, cleaning process. One thing is you can take a processed file and work on that and do photometry and other things to that. And yeah, you can take observations of clusters or look at the, find out, plot them on the HR diagram, see the turnoff points and establish the age of it and various things. Yeah, so essentially we are using it for uh, observations where you are not having archival data, but you actually observe the data and you work on it. So many people are more interested that this is what we thought we will do, this is what we observed, and this is my data. Yeah, so this is a good opportunity to observe yourself without having a telescope in your backyard. And yeah, so this is some self propaganda and various things can be done. Okay, so uh, I'll stop this share now and I will go to sharing the whole screen. And okay, so okay, you have this about this LCO. Yeah, Wikipedia gives you all details of and so on. Hmm? You can a lot of information available, and if you want LCO archives, we have this LCO archives. Yeah, so here you have your so you can various resources are there. Education with LCO, science with LCO. There are projects there. There are science teams. There are seminars, conferences, which you can have a look, and you can get science archives. Okay, so here are the archives. If you have a login name, you can log in here. But yes, you can log in and specify what you would like to observe, what days, between what day to what day, and so on. Otherwise, you can say some object, say M M31, and obviously M31 I gave because it's something very interesting for all, and I was expecting data would be available. And here is the list. You have these are all of M31. Date, should I expand this a bit? Okay, so it tells you when it was, these are different files. It says the time it was observed, where did the proposal come from, object name is this one, and exposure time. Exposure time is there, and then here it says it is raw or banzai. The raw ones are the raw data frames, unprocessed ones, which you can download and use to practice, while the banzai, which have gone through the banzai ones, are the processed ones. Okay, so when you are doing that, yeah, then it also tells you which filter. You have V filter here, you have B filter here. Okay, so each one you have the raw and the banzai ones, and you can download them. So, and to keep an eye on the exposure time. the longer the exposure, it should be better, right? Here is 9.9, while this is 599, 299. So pick up a larger exposure, preferably. So I take, say, B and also V. You just tick those and you say download. So you can tick as many as you want if you want to clutter up your computer. Otherwise, you can download specifically what you are interested in, and it's going to download. Okay, so it's coming as one zip file, and okay, so it is sitting here in my downloads. Yeah, it's your default location, and this is you can unzip it, and you'll see that there are two files here, right? So one way of doing it is just copy it and move it to the location where you want. Where should I move it? Say in Manu workshop, and okay, so we have moved it at a certain location. And the name, as you saw, was something very strange, isn't it? Yeah, the names, I don't know whether you can see them, but it says OGG 0M406 KB27 203. So there's a way it labels it, where the date is specified and so on and so forth. But you see that we have taken this E00, which was a bad choice. I should have. It is I have taken the raw images by mistake, but I should take the ones which have been processed through Banzai. So let me do that. Hmm? Hmm. Yeah. So see, there are E00 are the raw ones, E91, which ends with 91 other, and actually it shows there on the right hand extreme column, it says Banzai, and uh, we download it. And then how do we see these .fz files? These are compressed files. So either DS9 can open it, or Python can open it, or there is a tool which unzips this funzip tool, which you have to install and you can unzip it, or you can open it in DS9 and save it as a simple fits file if you want. Okay, right? It's a further compressed file, but in Python you can use directly with this compressed file. You don't have to worry. Python will read it. Okay. So now we will go to our GitHub page and in Google Colab. So you can find one file in the GitHub page which says LCO IPy notebook. 5 minutes. Yeah. So I'll just rush you through and yeah. So this is the file. Matplotlib inline yeah. So more important is this astropy, numpy, fits. Yeah. As of now, we want this fits. So from astropy IO import fits. So this will help us read fits files. Okay. The other things, matplotlib and other things are to do other stuff. Okay. And APL pi is also what we will require now. Hmm? Not Priya's on mine. So you go to, or Priya, from yours you transfer it, mine to yours. Okay, so and when I run this, I may get a error. Okay, so don't panic. You, I'm running it. So basically from astropy.io, yeah. So see, there is some error. It doesn't know what APL pi is. Okay, yeah. So it tells you what is the problem. And what you'll have to do is you have to pip install this APL pi. And if you are doing it in your Jupyter notebook on your system, then once you have done it, next time you don't have to worry. In Collab, you'll have to keep doing it. Okay. So pip install here. And in fact, in the same GitHub page, there is one tutorial. We have many AstroPy 1, 2, 3, 4. We could only touch upon units 1 and coordinates 2. But you go through 3 and 4, and as you understand, read it, you'll understand. Okay. And in fact, some of you have already done that. So it has finished. Yeah, it has successfully installed this thing now. So as of now, I'll put this off and I'll rerun this one. Okay. And this time I shouldn't have a error. So there, it came out clean. This is commented, so it won't give you anything. And now yeah, I am, yeah. So actually, I'm just calling this file name equal to this file. Okay, I'll have to upload the file. So we'll have to upload, click that, and you'll have to upload the file, and I'll have to go to whichever location, and here's my thing, and I open it. It gives you a warning, and it is uploading it. Here it's the circle is partially done. Yeah, so by the time it's uploading, I'll just show you. Here I'm calling this whatever file I'm going to read here, this fits.fz. Uh, I'm writing it into a variable called file name, and I'm reading feeds.open file name. I needn't have done that. I could have written directly that file name in the round brackets here. Okay. Yes. So it is uploading still. So we'll have to be a bit. Okay. So once it is done, we will read fits.open. We'll open that file. And then when you run this HDU info, yeah, so we are opening that file and saving it in this variable name called HDU, right? You can give, and in when you run this .info command, it tells you the different. It's a fits file which has, like we said, no, Banzai creates a primary, one science image, one bad pixel mask, and the error. You see, these are the four things which is created. Uh, and yeah, this is giving you some basic information. For each HDU slice 0, 1, 2, 3, the first one is labeled 0. I can further see the HDU 0 header, HDU 1 header, and it will tell me what these different slices are and the header information. Okay. So this one, in this case, not the primary, the science is the science image there. Yeah. So either you give the name in brackets, you in comma, you specify the name, or easier is to give this number, and this is the header information, right? It's, you can go through this header and it will tell you all these things. uh, RA declination of the system, location of the object, of exposure time, various things it gives. And then when I look at this HDU, yeah, so I'm saving this HDU1. When I know that slice 1 is the image, this HDU1, I'm renaming it as, I'm giving it a name, HDU underscore image. You can call it just image if you wish, right? If you can just call it image. And then when you say dot data, it will print you this matrix. So basically that image, what you have is collection of numbers. How many photons which are sitting on each pixel. So any image on a CCD is basically a matrix. If there is nothing registered, no light has fallen, it is 0, right? So there are some numbers, and right. So an image is nothing but, and then you can plot im show, and you specify the scale which you want, the color maps which you want, and this alpha will define the value. And you will see that you can change the contrast and see there's something sitting here, right? And there are various color maps: inferno, plasma, magma, CVD waves, the various. uh, in Matplotlib, there are various color maps which you can use. On those scales, you can see those exactly like you do it on DS9 also, and you can, right. So basically, this is it. Uh, you can freely use that file, and we will make changes to it and add other aspects to it uh, in time to come. So you can always go into the repository and see. Okay. So with this, I'll stop. Thank you. Yeah, Mudassir.
Yeah. We'll start with the student presentations. And as we continue to walk through, how many will we finish? Otherwise, we do the rest. So yeah, you are supposed to use 10, 15 minutes max, 15 minutes. So this is so now you'll be able to share. So इसी में बात करो. Start your video here. Yeah.